Hello, welcome to the introductory video 311 for Spectroscopy and the Electromagnetic Spectrum for Pre-AP Chemistry curriculum. We will start by talking about the atomic emission spectra. Based on this picture, what do you think gives gas, feel, light these different colors? Well, it's quite simple. If you walk in the evening along a busy street lined with shops and theaters, you are likely to see advertising signs like this. The signs are formed from glass tubes bent into the different shapes, as you can see. An electric current passing through the gas in each glass tube makes the gas glow with its own characteristic color. Rather curiously, the quantum mechanical model grew out of the study of light by Isaac Newton. He tried to explain what was known about the behavior of light by assuming that light consists of particles. However, there was enough experimental evidence to convince scientists that light consists of waves. The figure shown, as you can see, illustrates some of the properties of waves. As shown, each complete wave cycle starts by 0 on the y-axis, increases to its highest value, passes through 0 to reach its lowest value, and returns to 0 again. The amplitude of a wave is the wave's height from 0 to the crest. The wavelength, it is represented by lambda, the Greek letter. It is the distance between the crests. The frequency, represented by the Greek letter nu, it is the number of wave cycles to pass a given point per unit of time. The units of frequency are usually cycles per second. The International System units of cycle per second, it is called hertz. A hertz can also be expressed as a reciprocal seconds raised to -1. The frequency nu and the wavelength lambda of light are inversely proportional to each other. As the wavelength increases, the frequency decreases. According to the wave model previously shown, light consists of electromagnetic waves. Electromagnetic radiation includes radio waves, microwaves, infrared waves, visible light, ultraviolet waves, X-rays, and gamma rays. The electromagnetic spectrum consists of radiation over a broad range of wavelengths. In the visible spectrum, as you can see, red light has the longest wavelength and the lowest frequency. If we go back to the beginning of this video, we can conclude that the sun and the incandescent light bulbs emit white light, which consists of light with a continuous range of wavelengths and frequencies. According to the wave model previously shown, light consists of electromagnetic waves. The wavelengths of the spectral lines are characteristic of the element and then make up the atomic emission spectrum of this element. When electric current is passed through a gaseous element or through the vapor of a liquid or solid element, the electrons of atoms of the gas or vapor are energized. This energy causes them to emit light. When atoms absorb energy, their electrons move to higher energy levels. These electrons lose energy by emitting light when they return to lower energy levels. The energy absorbed by an electron to move its current energy level to a higher energy level, it is identical to the energy of the light emitted by the electron as it drops back to its original energy level. However, when the light emitted by the energized electrons of a gaseous element is passed through a prism, as shown in this figure, the spectrum consists of a limited number of narrow lines of light. As shown in this figure, the spectrum consists of a limited number of narrow lines of light. The wavelengths of these spectral lines are characteristic of an element, and they make up the atomic emission spectrum of the element. The atomic emission spectrum of each element is like a person's fingerprint. Just as no two people have the same fingerprint, no two elements have the same atomic emission spectrum. In the same way that fingerprints identify people, atomic emission spectra are useful for identifying elements. This figure shows the characteristic colors emitted by sodium in A and by mercury in B. Much of the knowledge about the composition of the universe comes from studying this, the atomic emission spectra of the different stars, which are hot, glowing bodies of gases. Now, hands-on. Calculate the wavelength of yellow light emitted by a sodium lamp if we have the value for frequency. For this example, we will write the expression that relates the frequency and wavelength of light. Then, we will rearrange the equation to solve for lambda. Finally, we will substitute the known values for nu and the constant into the equation and solve. Thank you for watching the video as an introduction for this topic. Next time will be all for electric effect to determine the structure and concentration in a mixture of chemical species by spectroscopy, so be ready. If you have questions, please do not hesitate to contact me. Bye, leaders!